So with each of these vectors, the magnitude we can think of as the length of the line. Okay, so we'll be calculating lengths, and the direction, like it says here, is always relative to the positive x-axis. Okay, so when we're asked to find a direction or an angle, we are creating our angle from 0 degrees, which is the positive x-axis. Okay, that's important to remember because sometimes 0 is due north, and due north is the positive y-axis. But for vectors, as we state them, without them being bearing problems, vectors have 0 degrees as the positive x-axis. Okay, so let's look at some things that we're asked to do. So here we have a vector in component form, where the 9 in this case is your x component, and the 12 is your y component. Okay, so we can put this on a coordinate grid where it says go 9 units to the right and go 12 units up. So our vector is going to start at the origin, and it's going to end out here at the coordinate point 9, 12. And we represent the vector with a line that has an arrow at the end pointing to the coordinate that it's going to. So now that we've seen it, let's figure out the magnitude. So in other words, the length of this line. So we're going to call this, right, this is vector v. We're going to find its x coordinate, or its, no, we're going to use the x coordinate, and we're going to use the y, because these are now legs of a right triangle. And anytime we have a right triangle, we're trying to find the hypotenuse, we can use the Pythagorean theorem. So the form says you take the magnitude of v, and this double bars here on both sides, that's the symbolic representation for magnitude. So if you see the letter inside of these double bars, that is telling you to find the magnitude of that vector. And it's done by using the Pythagorean theorem, which says 9 squared plus 12 squared. Right? Your x component squared plus your y component squared. So when we plug this into our calculator, I get that the vector has a magnitude of 15. And since there aren't any units, then we're just going to leave this as 15. So we don't know if it's newtons or pounds or foot-pounds or whatever it happens to be. So 15 is the magnitude of this vector. Now the direction is once again the angle from the positive x. So if we're looking at this, maybe you remember your trigonometry, y is the opposite side for our angle, and x is the adjacent side for your angle, which means we're going to set up a tangent ratio. So the tangent of the angle is the opposite side, or the y side, over the x, which is 9. So the tangent of our angle is 12 over 9. And anytime we want to solve for an angle, we take the inverse trig. So the inverse trig, or inverse tan, of 12 over 9. We plug that into your calculator, and you round to 1 decimal. 53.1 is the direction, right? So whenever we say direction, we are assuming that it starts at the positive x and it's going up. Okay, so there we have it in component form. What if we have something that looks like this? Okay, this is called a linear combination, which is written more like an equation. But the -6, well, that's still your x component, and the 4 is your y component. So when we draw this on our axes, we're going to go 6 units to the left, right? It says -6 in the I direction, which is your x direction, and then it says go 4 in the y direction. Okay, so our vector is going to end up here at -6 and 4. So this is the representation of our vector. Starts at the origin and ends at the coordinate -6, +4. So once again, to find the magnitude, we're going to look at the y side of 4 and the x side of 6. And this is going to help us to do the, well, it's called the magnitude. So our double bars, the square root of -6 squared plus 4 squared. So this becomes positive 36 plus 16, which is the square root of 52. So let's plug this into our calculator and then we'll round to 3 decimal places. And there is our answer. So now let's find out what the direction is, or our angle. Now look at where our right triangle is positioned. With our right triangle, we're able to find this angle. Okay, but that's not the angle we want. We want to know what is the angle in relation to the positive x-axis. So this needs to be our answer, right? This is our angle. So we cannot find this directly, so we'll first find this triangle angle, and then since these two make a linear pair, we will subtract the one that we calculate from 180. Okay, so we always use the inverse tan because this is the numbers that we have. So inverse tan of 4/6. Okay, we'll just keep it positive since it's above the y-axis. The inverse tangent of 4/6. So now that we know that, we can find our direction from the positive x-axis by subtracting the angle that we just found from 180 degrees. Okay, and we do this because we want to know what is the angle with the positive x-axis. So this turns out to be 146.3. Okay, so depending on the quadrant of your triangle, if your triangle is in the second quadrant, we're going to end up subtracting the angle from 180. If your triangle is in the third quadrant, we're going to add the angle to 180. And if the triangle is in the fourth quadrant, we're going to subtract our angle from 360. So it depends on where your triangle is as to what operation you're going to do to get your angle. Okay, so let's see if we can go the opposite direction. So these ones say write each vector in component form. So you're given a magnitude and a direction, and we want to write it as a component. So once again, let's go to our xy axis. Okay, so we have a 40 magnitude vector at a 35-degree angle. So we're going to come up from the positive x-axis 35 degrees, and your vector is going to be however long you want to make it. So 40 is the magnitude of this vector. So we need to change this into its components. So here we have the x component, right? The x side, the horizontal distance traveled. That's the x component. And we also have the vertical distance traveled, which is your y component. So once again, notice that we have a right triangle. And whenever we have an angle and a side, right, this would be the hypotenuse. We can use trigonometry to find our other sides. So the y value is the opposite side, and the x is going to be your adjacent side. So let's find x first, since it comes first in your component form. So if x is the adjacent side and we know the hypotenuse, that means we can set up a cosine ratio. The cosine of 35 is a comparison of the adjacent side, which is x, to the hypotenuse, which is 40. We are always going to set up a cosine ratio anytime you're solving for the adjacent side, which is your x value. So if we're going to solve this for x, we'll multiply both sides by 40, and it turns out x is always the magnitude of your vector times the cosine of your direction, the cosine of your angle. Okay, we can do a similar thing to find your y component, right? Y is the opposite side, so I can set up a sine ratio. Sine of 35 equals y over 40. And once again, we will multiply both sides by 40, and we have the magnitude of your vector times the sine of your angle. Okay, this is always true. These are always the calculations that you're going to do in order to change from a magnitude and direction into a component. And we'll see down there at E and F, that is a very handy way to handle applications, is to change them from magnitude and vectors into components. So let's go to our calculator and let's see what 40 cosine of 35 and 40 sine of 35 happen to be. So these are the two values that we get from our calculator, 32.766 and 22.943. Okay, so that's an important skill to have, to be able to change a magnitude and direction vector into a component vector. Because there's things we do with components that we can't do with magnitude and direction. So 312 degrees, that would be 90, 180, 270, 312 is over here in the fourth quadrant somewhere. Okay, so then we have our vector that has a magnitude of 22. So once again, we're going to find the x component, which is your horizontal, and we're going to find the y component, which is your vertical. Okay, so let's go straight to it. We know, hopefully, that the x component is the magnitude, which is 22, times the cosine of your angle, 312 degrees. And the y value is the magnitude, 22, times the sine of your angle, 312 degrees. Now, as long as your calculator is in degree mode, it should give you the correct answers. And then just round it to 3 decimal places. Okay, so notice that the y value came out to be negative, which is exactly what we expect if our vector is in the fourth quadrant. In the fourth quadrant, we have positive x values and negative y values. Okay, so that's why this came out to be a negative, because our vector is terminating in the fourth quadrant. And your calculator tells you that when we did sine of 312. That's a negative value. Very good. Okay, so now let's use this skill of changing from a coordinate to, a angle and direction to a component to work on these two application problems. So it says we have forces of 15 newtons and 22 newtons acting on a body at an angle of 72 degrees. So that's the angle between our two vectors of 15 and 22. Find the magnitude and direction of the resultant force. Okay, so let's once again start by drawing these. Now we're going to put this on here with some strategy. And the strategy is put your first vector, so this one here of 15 newtons, put it directly along your x-axis. Okay, so this is going to save us when we start doing our calculations. So this is our 15 Newton vector. And now we put in our other vector. It says 22 at an angle of 72 degrees. So from our 15, we come up 72 degrees. And this is your 22 Newton vector. Now draw it longer than your 15, because 22 newtons is a greater force than 15 newtons. So if you want your eyeballs to believe your math, make it look artistically correct. Now, to get a visual, we're going to create a parallelogram out of these two vectors. So we're going to bring our 15 Newton vector up here to the end of your 22. Right, and make it parallel and hopefully the same length. And we're going to do a similar thing with our 22 Newton vector, make it parallel and hopefully the same length. Because your answer, your resultant, starts back here at the origin, at the beginning of these two vectors, and is the diagonal of your parallelogram. This is the movement of your body under these two forces. Okay, it would move along the diagonal of this parallelogram. So this R, this resultant, is the sum of our two vectors. So we're going to change our 15 and our 22 into components so we can add them together to then figure out what the magnitude of our resultant is. Okay? And this is why we did this. If I'm going to change my 15, okay, because I made it go directly right, that is all of the forces acting in the x direction and none of the forces acting in the y direction, because we drew it going directly to the right along the positive x-axis, which has a value of 0 in the y. So our 15 Newton force becomes the components vector 15, 0. We did that on purpose. Now the 22, right? This one we're going to have to change using trig because it's acting at a 72-degree angle. So what we did before is you take your magnitude and you multiply it by the cosine of the angle, right? And that will give us our x component. And we do 22 times the sine of 72, and that will give us our y component. So let's put that in our calculator real quick so that we can figure out what this is as a decimal. So now we're going to add these two vectors together to figure out what the component form of your resultant is. So I do the x component, which is 15, plus my x component, which is 6.798, and that gives me 21.798. And I do the same thing for my y stuff. So here I have a y of 0 plus 20.932. Well, I like adding to 0. That's okay. 20.932. So these are the components of my vector. This is my x component, and that's my y component. So just like we did with letters A and B up above, now that I have my component form, I can use the Pythagorean theorem in order to figure out what the magnitude is. So the magnitude of R is the square root of the x coordinate down there, which is 21.798, plus my y component of 20.932. So there's your answer, and our units are in newtons, so 30.221 newtons. Now to find the direction. So the direction is always the inverse tan of the y component over the x component. Okay, so just like we did up above, we're going to use your y and your x, these purple things, because I wrote them in purple, and figure out what the angle is going to be for our resultant. So 43.8 degrees. So let's see if that matches up with what we have over here. Right, I can believe that it's less than 72, sort of in the middle-ish, so I believe that would be a great answer. Okay, in our last example, we have two forces that are acting on different angles. Okay, so we have a 10 magnitude vector with a 15-degree angle and a 25 magnitude vector with a 65-degree angle. Okay, so when we do our parallelogram method, we can make a pictorial representation of the resultant of this vector sum, right? We're adding these two vectors together. So it looks like our vector is going to go from the origin to the diagonal of this parallelogram. Okay. So notice that they're both acting on angles, so we're going to have to do conversions for both of them. So for our 10 magnitude vector, that's 10 times the cosine of 15 and 10 times the sine of 15 degrees. Okay, we're converting from a magnitude and direction into component form. 25 cosine of 65 and 25 sine of 65. Okay, so we're going to convert both of those into their decimal components and then add their x's together to get the components for your resultant. Okay, pause the video and go ahead and do those calculations. Okay, there are all of the decimal conversions. Okay, now we're going to take this wonderful component form and we're going to find its magnitude, okay, which is done with the Pythagorean theorem, your x component squared plus your y component squared. And also we're going to find the angle by doing the inverse tan of the y component over the x component. And those are the calculations that I get from my calculator. Okay, remember, when we're converting, the x component is always the magnitude times the cosine of your angle. And the y component is always the magnitude times the sine of your angle. And then you find the magnitude of your resultant by doing the Pythagorean theorem, and the direction is the inverse tan of the y component over the x component. All right, great job. Have a wonderful day.